Welcome to the first steps in debugging. Before now you should have learnt how to load a file, compile, and then load said file that's compiled and got no errors into Komodo. So again we're going to go over the three areas of Komodo before we start the concept of debugging. So this top window is where you load in the program. And as you can see, it's got some different coloured lines. Well, it's got black and green. This green line points to where the program counter is. So here's the program counter in the register set, and it's pointing at address 0. So this is where the source code is loaded when you press this button. Now at the same time, you have a view of the memory. Now remember, these two are slightly different. This is the source code here that you will have written, so you'll be familiar with this, and this is the equivalent hex that's loaded into memory at these specific addresses. Now if we go down here, we're looking at the memory. Here are the memory addresses. Now these symbolics on the right are not the same as these. This is the program you've written and is human understandable and is probably coded correctly for a mapping to the correct symbols. Whereas this is not. This is a disassembly of this. So make sure you understand that. This is the code you've written. When you press the assemble button, that name is wrong, it's assemble, you get this code, which is hex, and it's placed in memory. This is the memory window. So how can we see this data then when you've got a number of named variables, and here they are, they're defined by a word here? Well, the way to see them in the memory is press this toggle button here. Now you can see any labels, and here's one, loop, in the memory. So let's just go back. If you haven't toggled this, you will see the memory addresses. Once you've toggled this, you will see any labels which you jump to, or back to, or forward to, and then any variables as well. So here are your variables, and now you'll see that when you look at these variables, loop count is given a value here in memory of 3. So let's go up here, and you can see it's defined as 3. But now look at this. This is not the code that you would expect when you wrote the code, and this is because this is the code you loaded in and wrote. This is the memory, this is a disassembly of the memory. And you'll see straight away that the memory uses pointers to addresses, whereas this source window uses variable names and, if you've got any loops, loop names as well. Okay, so we've done those two windows. This is the source window. This is the memory, and these are the registers. So how do we debug then? And why is it essential that we need to know how to debug? Well, when a program's not working, it shows that some of your algorithmics are probably wrong, or your data structure is wrong. So realistically, a computation course should teach you first data structures, design, implementation and visualization, and then algorithmics, design, implementation and evaluation. Now if you don't understand these concepts, you'll tend to become a hacker, and for some strange reason we're having hacking competitions, which has nothing to do with computing. It means you don't understand computers if you're a hacker. It means you don't understand the basics of data structures, algorithmics and software engineering, which is extremely bad. So, what can we do to explain how debugging helps you understand about the algorithmics, the data flow, and the processing of data? Well, the first thing you've got to realize, to algorithmically process the data that's placed in memory here, it is moved from this memory window here, and here is the data. As you see, there's a loop count, increment results 1 and 0, values which are data items, these are physically moved to registers. So the first thing we're going to do when we learn debugging is look at some instructions that actually undertake these moves and understand that we can visualize the movement of data from the memory at specific addresses to the registers. And this is called register loading. So let's do that then. Let's have a look at the source window and have a look at this instruction. So, what do we expect? So if we read this instruction, we should be able to predict the expected outcome at the end of execution of this instruction. So let's read it step by step, reading the symbolic notation or the mnemonics and then predicting a result. So this is a load instruction, and a load has two arguments, if you like. One is where to put the data and one is where to get the data. So this is a register address. So as you know, these are the registers and this is the explicit register we're talking about. So the first thing to notice is initially this register is, its initial value that is 0. So what's happening here? Well, in this source implementation we're taking the variable result and moving it into, or loading it into R0. So if you look at this, we're going to result and it has a value 0, so we're going to move 0 into R0. So we won't actually see any change, but it will be loading 0. So let's have a look at this then. Here we've got the memory mapping of this. So here we're loading R0 with and from address hex 30. So if we change this back to addresses and go to 30, it's that one. So 30 says we've got a value of 0. Now we'll move it back to symbolics. So we've got results, and it's 0. So what I'm going to do now is press the single step button here. But before I do that, we're going to expect and predict the value. The value here after the instruction is going to be 0. So let's undertake that single step operation. Now, the first thing that's happened is we've taken this data, which is result, here, and we've moved it to R0, and as you expect, it's got 0. Now, the thing I should have said is we can actually watch the program counter. Previously, the program counter, this pointer here, which outlines this line here in green, was pointing at address 0. Let's go and have a look at it. Now it's pointing at address 4. Now this is extremely important that you understand the process flow of watching the program counter when you undertake any branches, because the program counter should point to the next instruction, which is this one, and if you follow it, it should branch the appropriate instruction that you've told it to in your algorithmics. So, what have we found out so far from debugging? Well, we've seen straight away that we've got some color changes. These black text here, implicitly, though it hasn't been explicitly said, tell us this has not been run. This green line here and here tell us this is the next instruction. Now implicitly this blue one might be telling us actually this instruction has been executed. So let's look at the next instruction, look at the address and predict what's going to happen. So we'll change it back to addresses. This is 2C, so 2C is 4. Let's move it back to symbolics and see what that is. Let's first go to here and say it's increment. So this increment value is 4, and it says that we're going to load it into R1. So let's go and run this instruction and see the value of R1 change. So we're single stepping and we're watching registers and we're watching the program counter and seeing how the data moves from this memory here into the appropriate and correct register. So let's single step to there then. So what did we expect? Well, we expect the previous instruction here, which loads this data, which as we know is increment, into R1. And increment is 4. So we expect R1 to be loaded with 4. And as you can see, that instruction has actually loaded R1 with 4. Now we're going to step through these a little bit faster. So the next thing we're going to do is load R2 with loop count. Loop count is 3, and load R3 R3 with 1 and R4 with 0. So let's just quickly step through those and see the data transferred from memory here to register here, and we're going to single step them again. So we're going to step over, step over, step over. Now what we've done, we've seen that all the data now has been loaded from memory, from here, into registers. So we see that all the registers R0 to R4 have been loaded with values. Now we can check that they're the appropriate values by checking with this code. So the results R0 should be 0, and it is. The increment R1 should be 4, and it is. The loop count R2 should be 3, and it is. 1 should be 1 in R3, and it is. And 0 should be in R4, and there's 0, and it is in R4. Now this is called the initialization of data structures phase. So here we've taken the data and we've initialized the registers ready to do algorithmic processing of the data structure. In fact, what we've done is we've copied the data structure from the memory into registers. Registers are much faster, so now we're going to process the data. So let's have a quick look at what's happening here. Now the whole idea of single stepping is you watch the data, but previously, if you like, you could do this on paper. Down here you could draw up a number of columns and draw up, say, the R0 register values and R2, and previously work them out on paper what they should be if you expect your algorithms working correctly, and then check that your registers actually follow that pattern. So let's single step through this program. First thing to realize is we are pointing at an iterative loop, and the iterative loop is here. Now hopefully you understand what's happening here. If not, we might leave that to a bit later and say, well, okay, what if you didn't understand what's happening? Could you go and watch these registers and see each instruction running step by step and then work out what's happening? Because that might lead you to fixing a bug. So let's first go and see what this is. So this instruction here, let's just run this instruction. So we're going to move this program counter, which is pointing at address 14, which it is, to the next location and run the present instruction. So that's single step. So this single step has now performed an instruction. Let's validate the instruction has been performed correctly and we've got the correct data. So it says add to R0 R1 and then place the data in R0. So let's go and have a look and say, well, previously R0 and R1, R0 was 0 and R1 was 4. So we've actually added 4 to R0. Let's go and check R0, and that is the correct result. Now we're pointing at the next instruction. Let's quickly check these registers. Let's have a look at R2 and R3 before we run the instruction, which is a subtract. So R2 is 3 and R3 is 1. Now let's run the instruction and see how it changes this data. So what's happened? We've subtracted R2 and we've subtracted from it R3. So it was 3 in R2, we've subtracted 1 from it, and now R2 is correct, it's 2. Okay, so we think this is all working, that's good. Now what do we do? Now what it does is it's doing a check. It's saying if R2, or it's actually not doing a check until it gets the break, it's just doing a compare. It compares R2 and R4. So let's go and have a look at R2. R2 is 2, R4 is 0. So if you do that simple subtraction, which is basically what it is, R2 minus R4, and you'll see that if you do it, it's not 0, and you will branch back to this address 14, which is actually the loop. So let's undertake the compare, but before we do that, let's look at these conditions code, because what the compare does is set the conditions code. So one of the things that you can do is you can toggle all these codes and then see what this compare does to it. So all I've done is I've set them in one state. Now I'm going to run this compare, and it's going to compare two registers, R2 and R4. Let's do that and see what happens to the conditions code flag. So you see that the carry has changed. All the others have not. So what are they telling us then? Well, I think this interprets as being set when it's like this. So let's look at the flags then. First one to see is this 0 flag is set when you compare 0 and 0, and the result is 0. Now it's not, because you're comparing R2 and R4. R2 is 2 and R4 is 0, so they're obviously not equal. So I would say this one is not set, the negative is not set, whereas the carry is. So the operation has been undertaken. We have a carry out of the ALU. So at the moment it says in the next one's branch not equal to 0. Well, at the present time the 0 flag is not set, so it's not equal to 0. So we expect this result of this compare and this branch to branch back to the loop. So that's what we expect to happen. So now what we're going to do is watch this program counter. So we look at the program counter, which is set at 20, and we expect it to jump back to here. So let's just quickly put this back into numbers. So we expect after this branch, when it's checked these conditions, particularly that 0 flag, which is not set, because the two registers were not equal, we expect the program counter to move from here back to here. Let's single step it and debug it to prove that our prediction is correct. And it has moved back to here, and the program counter, as you saw, was loaded with the loop label address of 14. Now let's single step through these again and see what's happening. Now what it's going to do, it's going to keep adding to R0, and this item here, R2, which is what we've called our loop counter, is going to be decremented. So let's step through, quickly watch these registers and see if it jumps back to the loop label each time after the branch. So here we go. We're going to jump through the add and check what happens. So single step, we've added another 4 to this register because that's what it did. And then the next thing we're going to is decrement this loop count. So it's 2 at the moment, and we've decremented to 1. Then we do a compare again. So let's put these in inverse this time. So we're going to inverse all of these. So just see them change. Now we're going to do this compare. So let's do the compare. Now you'll see all of these changed. Well, some of them. And you'll see again this 0 bit is not set. The carry flag is, and the other 2 are set. So now what do we expect to happen here? Well, we expect it to jump back again and change the program counter from 20 to 14. So again, there's 20. Let's check this, and it goes back to 14. Now let's do it once more, and then it might end. So again, we're adding, so that's single step. We've added another 4 that goes up to C. Now we're going to decrement R2 by 1, so that's decrement R2, so we're single step. That's interesting, R2 is now 0. So we're going to have something totally different now. So what we've got to do then is I'm going to set all of these to this condition to see what happens when we do this compare. Now we're going to compare R2 with R4. R2 is 0. R4 is 0. Let's see what happens to these conditions code flags now in this compare. So we go single step, and we see straight away this time the 0 flag is set. It basically says, in the operation I've just undertaken, the compare, these two values, R4 and R2, are exactly the same. Okay, now let's see what the branch will do. Now you can predict this. I'm not going to give you any hints or anything. What should happen now? So we're going to single step through the branch. Is the conditions code set up to branch back to the loop or not? So that's single step. And the answer is it's not. We've actually fully undertaken the algorithm. We're just about to stop now. So now you see that what we've actually done is a number of operations. We've single stepped all the way through the program, watching the registers correctly change the appropriate values and even predicting them, and watching how the program counter moves us back to the appropriate loop label if a branch condition is correctly met, and watch the conditions codes. So again, the important thing about debugging is we can watch the process flow. So I'm going to go and do one more debugging phase and introduce the concept of a breakpoint. So again, what we're going to do is load the program, and this should load all the values fresh. We're going to reset all the values. Now we should be back to the start, but what we're going to do now is we're going to put a breakpoint. So as you can see, it highlights a breakpoint by changing the color of the instruction line and address. So what's a breakpoint? Okay, well if you're not sure, what I'll do is I'll just run to it and then explain it. So what we're going to do is, instead of pressing single step, we're going to press run. Now what's happened, it's gone through all these instructions, carried out all the transfers of data from the memory here to the registers, and performed any algorithmic processing. And it's done one set of algorithmic processing, one added 4, and one subtraction. Now we're in a compare. So what you can do with a single step is you can position where you want to stop. So in a complex algorithm, you can say, okay, I've branched to a part of the algorithm. I don't want to go through any of the other parts of the algorithm, but I want to see what's happening here. So what you do is you place a breakpoint, and now we can single step. So that's just what we might be predicated on here is this conditions code in this branch, conditional branch, acting as I'd expect? And the premise here is it if this condition is that it sets the 0 flag, which it's checking branch not equal to 0, is it going to branch correctly? Well, let's look and say, well, let's check the data to see what we'd expect to happen. So R2 and R4, it's going to compare them. R2, R4, 0 and 4, so they are not the same. Whichever way you do it, subtract one from the other, you will get a non-zero result. Okay, so let's undertake the single stepping of the compare. Now the first thing that happens is we'll get some condition codes registered. So the first thing, if we look at that, the 0 bit has not been set, so the outcome of that instruction is not that the two were equal to 0. They are not. Okay, so this says branch not equal to 0. So hopefully, if this condition code conditional branch works, it should branch to 14 and branch back to here. So now what we're seeing is a little bit more eloquence in debugging. We've seen we've added a breakpoint. We've seen we can go into different parts of the code in different parts of the program and single step into it. Watch the condition code, watch the program counter, watch that the data is being algorithmically processed as we expect. So let's just check this branch and see if it goes to this address 24 or this one. And as you see, it goes to 14, which given these preconditions we would expect. So what have I just talked about? I've talked about the essence of debugging. But you cannot hack a program if it doesn't work. You have to understand the process flow. And the process flow is really the algorithmic process. So maybe what you should do before you start looking at code and not understanding what's happening is you should write it down in a high-level algorithm, and above that you should have the data structure that it's manipulating so you can understand how it algorithmically processes the data. So again, this is the data structure. which this routine algorithmically processes. It algorithmically processes it by first moving the data from memory here into registers in this initialization phase. It then goes through a loop instruction where it increments one of the registers by another, adding R1 to it, and it decrements another of the registers by subtracting R3 from it. And then it keeps comparing and branching it, saying, am I ready to stop yet? Am I ready to stop yet? It's an iterator. It's a loop. So what you need to understand is you can't have a branch without a compare, unless you make these conditional instructions, of course. So what we're doing here is the compare sets up the conditions code which the branch then checks and activates the branch, or ignores it and goes on to the next memory address. So I hope that's given you some insight into debugging. It's introduced a number of technical naming conventions. Single stepping was one, single stepping through the code. Another was the understanding of breakpoints. Prior to that, we introduced the concept of 3 different windows in Komodo. To remind you again, this is the code that you edit and then assemble. This is the disassembled code, disassembled from the memory addresses, and they're slightly different. The data here, let's change it to data. As you'd expect, these are the wrong instructions. They're just disassembled. So this disassembly is guessing these are instructions. They actually aren't. These ones are data. You can only see that in this top window where we've got the appropriate instructions and definitions of data structure storage here. So I'll say thank you very much for watching. Remember, if you watched this before the initial introduction to Komodo on paper and the initial first steps of programming, you should have watched those first, and then it would have given you context. Hopefully you've now understood the basics of debugging in Komodo. Thank you for listening.